Hello, ladies and gentlemen. I wish to present our preliminary results of our study of the skull biomechanics Metoposaurus Krasiejowensis skull from the Upper Triassic of Poland. The study is focused on the histological and computed finite element analysis investigations. And here the part relating to FEA analysis were done by my article co-partners, by Joseph and Mr. Jordan. The bone material used in this presentation comes from the Upper Triassic bone bed at Krasiejow, a few kilometers away from Opole city. The skeletal remains of the large vertebrates occur in two bone-bearing horizons of clay stones, and the lower horizon is still being exploited currently, and the remains of the large spondyl amphibian Metoposaurus are the most common here. Metoposaurids were a large, around 2-3 meters long, aquatic late Triassic temnospondyls with a dorso-ventrally flattened body. And the most characteristic and the best known part of the Metoposaurus skeleton is huge, flat and a parabolic skull. And until now, the feeding mode in these animals was mysterious and unknown. Previously, the Metoposaurus was presented as an ambush predator which rapidly opened his jaw under the water and captured the prey by suction. And now I would like to present our results of the biomechanical study in the case of Metoposaurus, which show a quite different feeding mode in these animals. The bone materials used in this presentation constitutes of the large and well-preserved Metoposaurus skull, which was sectioned in 20 different areas. And the main goals of our study is to present the histovariability of different areas in the Metoposaurus Krasiejowensis skull, provide a new histological model of how the biomechanical loading works in different regions of the skull, and the last one, they correlate these histological results with the results obtained from computational mechanics using a three-dimensional finite element analysis. The results of these mechanical investigations, I think, may help to explain the other feeding adaptations, not only in the case of Metoposaurus, but also in the other temnospondyl taxa. The dermal bones ossify directly from a soft tissue, it means the deep part of dermis without a cartilaginous predecessor. And in temnospondyli, this bones creates the skull, the mandibles, and the pectoral gill. Their external surface is clearly ornamented by ridges and grooves, and in the cross sections, these bones show a diploid structure visible as a well-differentiated, compact external and internal cortices, which are separated by porous middle region. Biologically, every bone is a very dynamic structure, and its biomechanical properties we investigated on 4 histological levels. At the morphological level, it means at the shape of each bone, at the bone size and thickness. At the microstructural level, it means the relationship between the canceloporous and the cortical bone, and the last one at the nanoscale level, it means at the organization and types of the bone tissues. And in our study, we exclude the morphological level because almost all skull bones in Metoposaurus are the same and they are flat. And we also exclude the nanoscale level because the types of bone tissues and its organizations is very similar in all examined bones. However, the parameters like bone thickness and its porosity are the most variable feature on the entire length of the skull. We can say that the bone thickness is a biological response to the stress distribution, and we assume that the thick bones will possess a very good biomechanical resistance to stress distribution, and they, in this way, they indicate the particular place in the skull which were significantly involved in the feeding process. Here another factor which significantly influence on the biomechanical stress distribution is the bone porosity, because even the thick bones lose their strange and very good biomechanical properties just with increasing porosity. And so, in our study, to estimate the biomechanical properties of the skull, we use the bone profiler program to assess the relationship between the bone thickness and its porous. In this way, we accepted that these two parameters are were the most involved during the feeding process. And the histological results show that the skull from the anterior part of the skull, like premaxilla and maxilla, and from its posterior areas, like tabular and postparietal, are the thickest, up to 12 millimeters, and moderate porous. So it's followed that these bones were the best biomechanically resistant. Elsewhere, the bones from the central part of the skull, like for example nasal and parietal, are the thinnest, to around 5 millimeters, also moderate porous. So we assume that these bones were biomechanically the weaker. But in addition to this, the histological framework is not related only to the single bone, but strictly depend on the particular sectioning plane. For example, the jugal and postorbital bones sectioned at the sutural contact represent the same histological framework and demonstrate a very good biomechanical resistance. Another example, the squamosal bones, sectioned in two places, in its anterior part and next to the optic notch, maybe in a 2-3 centimeter distance, shows a completely different histological framework. So this suggests that the histological level is not specifically bone limited, but it seems that particular place in the skull which probably were significantly involved during the feeding process. And regarding to the palatal side, here every bone are also very thin and extremely porous. Here the erosion, like here as our example from vomer and pterygoid, here the erosion cavities reach to in a diameter to around 3 millimeters. So these bones represent the weakest capabilities to stress resist. And here the second goal of our study is present. I think that for the first time this correlation between these histological results with a three-dimensional computed finite element analysis. And here the three loading cases were analyzed, considering bilateral, unilateral, and lateral biting simulations. And FEA method shows that the Metoposaurus were very specialized feeders, using probably mainly the bilateral bite, maybe rarely the lateral strike, and clearly avoiding other biomechanical behaviors like unilateral bite, because as you can see, under these behaviors, the skull receives a comparatively huge amount of stress. So therefore, in our study, we compare only bilateral biting simulations with our histological results. And the FEA bilateral biting simulations suggest a very low level of stress in the anterior part of the skull, in the premaxilla and nasal areas. The thin sections taken from these areas also confirms the very good biomechanical resistance for premaxilla. The differences we can observe in the nasal and lacrimal bone, because in histological model these bones were estimated as biomechanically weak. Regarding palatal side, the bones like tabular and postparietal receives a low level of stress, and the same very good biomechanical properties was demonstrated by a histological model. Moreover, the moderate stress level is deducted for such bones like postorbital, frontal, and parietal, and moderate and a little higher level of stress could be loaded in such bones like quadrilojugal, supratemporal, and squamosal. And as you can see, in the case of the skull roof, both methodologies are almost compatible. Regarding to the palatal side, here, unfortunately, both models are divergent. The FEA model suggests a low and moderate stress in such bones like vomer, parasphenoid, and pterygoid. And unfortunately, in histological model, these bones are very thin, extremely porous, so they represent the weakest capabilities to stress resist. Actually, we don't know why in the case of the skull roof these results, in the palatal side, these results are divergent, and we will be working on this in the future. And at the end, I would like to show you my previous research on the same Metoposaurus skull, which focused on the cranial sutures. These structures play an important role in the skull biomechanics, and its morphology may help to interpret the feeding mode. And based on Marvey investigations on the cranial sutures in early tetrapods, here we have three main sutural morphotypes with different mechanical properties: the abutting, interdigitated, and overlapping. Each of these morphotypes is responsible for a specific method of a prey capture. And in the histologically analyzed skull of Metoposaurus, as you can see, only one sutural morphotype occurs, and this is interdigitated sutures of compression-resistant roll. Here are examples from postparietal bone. Here another example from the palatal side, another from the skull roof. And the presence of these sutures has been noted over almost on the entire length of the skull, both on the roof and on the palatal side. This type of suture is characteristic for terrestrial animals, which capture prey by biting instead by suction. So, as you can see, even the histological results, which focus on the cranial sutures, is compatible with bilateral biting simulation. And summarizing of my presentation, the current histological analysis show that microanatomical features like the bone thickness and its porosity significantly impact on the biomechanical stress distribution during the feeding process. The histological model, it means the relationship between the thickness and the bone thickness and its porosity, shows that biologically, the anterior and posterior areas of the Metoposaurus skull were the best adapted to stress resistance and probably were the most involved during the feeding process. And in the same, the bones from the central part of the skull roof and from the palatal side are the weakest, so they probably did not play a more significant role in the stress distribution. The histological model and FEA bilateral biting simulations are similar regarding the skull roof, and both methodologies are divergent in the case of the, mainly in the case from the palatal side. And the last one, the previous histological studies on the cranial sutures in the Metoposaurus also indicate that prey capture by beating in these animals, so maybe even like that. So these are, of course, our preliminary results, and we are still working on the final conclusions. In this conference abstract, we assume that the lateral model of FEA simulations are the most probably in the Metoposaurus. Now we know that it's not true. Our current histological and computational studies indicate that bilateral model the best overlaps with the bone histology, but the lateral model is almost optimal. So I hope that the next time I will be able to show you the final information about its mechanical functions with you.